Good evening, children.
Good evening.
Good evening.
Good evening.
Good evening.
Good evening, children. Good evening.
Good evening.
Good evening. I've shared my screen, children. Is it visible?
Yes,
Yes.
ma'am. Yes, ma'am.
All right, children. We discussed the definitions of orthocenter, centroid, incenter, circumcenter, and what these are in a equilateral triangle. You can see, just read the slides. What I would suggest is you can just write it again today so that you're reinforcing, it becomes practice and you can remember. You can even take it down with the figures here. I'll just wait for some time. So as you draw the triangle, as you draw this figure, as you draw these figures, you'll be reinforcing the definitions. Yes, do that. So this figure, children, in this figure, so you see this triangle ABC. This is the procedure to construct the incircle. You'll have to bisect the angles. See, the angles are bisected. Here, this angle is bisected. See, what you see here is the bisector of angle A. This one is the bisector of angle C. And this one is the bisector. This one is the bisector of angle B. To construct the incircle, we need to bisect the angles. This is the bisector of angle A. This is the bisector of angle B. This is the bisector of angle C. And you can see that the bisectors, they are concurrent. They go through the same point. They are concurrent. So this point of concurrence of the angular bisectors of a triangle is called the incenter. And this incenter is also the center of the incircle. See how this incircle is constructed. We are not going into that. An incircle is constructed. An incircle is constructed by bisecting the angles of a triangle. It's enough if we bisect any two angles. You don't have to bisect all the three. It's enough if we bisect any two angles. But you can see it here that when all the three angles are bisected, the angular bisectors, they go through the same point. So this point of concurrence of the angular bisectors of a triangle is called the incenter. And this is the center of the incircle. And here, what you see here are the perpendicular bisectors, not the altitudes. They are the perpendicular. What you see here, L1, line 2, and line 3. What you see here, line 1, L2, and L3, L1, L2, L3, line 1, line 2, and line 3. These three, okay, L1 is the perpendicular bisector of the side BC. It's the perpendicular bisector. Now, see, how do we do that? With B as center and radius more than half of BC, we cut an arc here and an arc below, an arc above BC and below BC. Then with C as center and the same radius, we cut the arc above and below BC. Then we join, right? That 4-arc method. We make 2 arcs above BC, we make 2 arcs below BC, and we join. That's what you see here. L1 is the perpendicular bisector of BC. L2 is the perpendicular bisector of AC. And L3 is the perpendicular bisector of AB. Altitudes are different. Altitudes will fall from the vertex. Or altitudes are different. Altitude falls from the vertex perpendicular to the opposite side. These are not altitudes. These are the perpendicular bisectors of the 3 sides of the triangle. And you can see that the perpendicular bisectors, they are concurrent. They go through the same point. And when do we construct the perpendicular bisectors? When we have to construct the circumcircle. So a circumcircle is constructed by drawing the perpendicular bisectors of any 2 sides of a triangle. Any 2 is enough. Here you can see all the 3. So to construct a circumcircle, we need to construct the perpendicular bisectors of any 2 sides of a triangle. Now here you see all the 3 perpendicular bisectors. They are concurrent. And this point is called the circumcenter. The point of concurrence of the perpendicular bisectors of the 3 sides of the triangle is called the circumcenter. Where the perpendicular bisectors meet, circumcenter. Where the angular bisectors meet, incenter. Incenter is also the center of the incircle. Circumcenter is also the center of the circumcircle. These are altitudes. See, from the vertex P, this line segment is an altitude from P to QR. It makes 90 degrees with QR. Similarly, QT is the altitude from Q on PR. RS is the altitude from R on PQ. These are altitudes. Altitudes are also concurrent. and this is the point of concurrence, where see more than two lines meet, right? More than two lines or line segments, when they meet, we say point of concurrence. So this point of concurrence of the three altitudes is called the orthocenter. And centroid, see here, these are the medians. This line segment is the median from A on BC. You can see it's, see here altitude, so they make 90 degrees with the base. You can see the, you can see the square which is marked here, indicating a right angle. So altitudes are perpendicular to the base. We know that. See, we know all this. Just, you know, assuring that you people know it, that's it. So you all know this. Now, so you can see that the altitudes are perpendicular to the base, and here these line segments are medians. So this is a median from A on BC, and median meets the opposite side at the midpoint. At the midpoint, so this point is the midpoint of BC. That's why it's marked. You can see these marked here, indicating that these two segments are equal. These two segments are equal because this is the midpoint. Similarly, this is the midpoint. These two pieces are equal. And this is the midpoint. These two pieces are equal. So from A, this is the median. From B, this is the median, because it meets the opposite side at its midpoint. And from C, this is the median, because it meets the opposite side at its midpoint. And you can see that the medians are concurrent. And this point of concurrence is called the centroid. So orthocenter, centroid, incenter, circumcenter. Now, all this applies to an equilateral triangle. How all this applies to an equilateral triangle? So here XYZ is an equilateral triangle. XYZ is an equilateral triangle. Now what happens is this line which you see, bisects X. So it's the angular bisector. And this one is also the perpendicular bisector of YZ. This XM is an altitude from X on YZ. And XM is also the median. So all those four lines, they coincide here. This XM bisects X. It's an angular bisector. XM is an altitude from X on YZ. XM is the median from X on YZ. So this is the altitude, this is the median, this also bisects X, and it's also the perpendicular bisector of YZ. It's also the perpendicular bisector of YZ. See, when you try to perform all these activities in an equilateral triangle, you try to draw all the three altitudes, and then you try to draw all the three medians. Then you bisect the angles, you bisect the three angles, you bisect the three sides, meaning you construct the perpendicular bisector of the three sides. Okay, so you in an equilateral triangle, you're trying to show all the altitudes, you're trying to show all the medians, you're trying to bisect all the three angles, and then you're trying to draw the perpendicular bisectors of all the three sides. When you do all these four activities in an equilateral triangle, when you do all these four activities in an equilateral triangle, you will see that the lines coincide. You understand? So I'm not repeating it. So this is what you see. So this point is the centroid. It's the orthocenter. It's the incenter, and it's the circumcenter. This one point is the incenter. It's an incenter I. It's a circumcenter C. It's the what is it? What is this G? It's a centroid G. And what's O? Doing an orthocenter. I'm doing it fast. I'm doing it fast, so I was not able to recall. Yes. Orthocenter O. This is the orthocenter O. It's an incenter I. It's a centroid G. It's a circumcenter C. This is what we saw yesterday. So, and now when you look at XM as the median, and G as the centroid. G divides XM in the ratio 2:1. This applies in every triangle. Somebody asked this question also yesterday. Is it only in an equilateral triangle that the centroid divides the median in the ratio 2:1? No, no. This property is in every triangle. But these four things coincide only in an equilateral triangle. These four things coincide only in an equilateral triangle. But that property, centroid divides the median in the ratio 2:1, applies to the median in any triangle. So when XM is the median, G centroid, G divides XM in the ratio 2:1. XG is two parts. GM is one part. It's not the other way. It's not GM two parts. From the vertex to the centroid is two parts. From the centroid to this to the midpoint of the opposite side, this one is one part. 2:1. Same thing here also. See here, YS is the median. YS is the median. G is a centroid on the median. G is a centroid on the median YS. Now, YG is to GS is equal to 2:1. YG is to GS is equal to 2:1. Similarly, ZG is to GN. ZG is to GN. We are saying G because G is a centroid. G is a centroid. So ZG is to GN is equal to 2:1. So children, I said I'll share the answer, then I was just occupied with some other work. I couldn't. One student also requested for the answer. I did not send. I'm sorry for that. I'll show you the answer now. Please complete the answer now, children. Please complete the answer now in the class. We discussed the answer. Please complete it now.
Ma'am, can you share the next slide, ma'am?
Yes,
Come
ma'am,
again?
yesterday you showed the slide, ma'am. We completed this part.
Oh, you finished writing also? Okay, I thought, okay.
The
Ma'am,
second
next
one we didn't
slide.
do, ma'am.
Okay, the next one, huh? All right, yeah. Nafi, are you in the class? Please text me if you cannot unmute and talk. Completed, children? Should I give you?
Yes, ma'am.
Finished? Okay.
Ma'am, I am doubt.
Yes.
Ma'am, have you multiplied the triangle into two, ma'am? Right triangle.
What have I done? Right triangle? No, what the working here is disable your mic, I'll tell you. Disable your mic. Yeah. What you see here is, let me explain using this slide. So the working there, we have found the area of this right triangle. We have found the area of this right triangle, and we have subtracted the area of this sector, and we have got the area of this half of the shaded region. So that answer into 2 will give you the area of the complete shaded region. That's what you see here. You can also find the area of the quadrilateral. You can find the area of the triangle, multiply by 2 to get the area of the quadrilateral. In that case, you need to subtract the area of this sector, to get the area of the shaded region. You can do it in 2 ways. So what you see here is I've found the area of the triangle, only one triangle, and found the area of the sector with angle 60 degrees, and found the area of half of the shaded region. Then double that answer to get the area of the shaded region. Is that fine?
Yes, ma'am. Okay, ma'am.
All right. Yes, children. We need to continue from the 7th one. We finished 1 to 6 yesterday. Please write down the 7th question. I'm preparing the paper on this chapter, areas related to circles. I think I also announced that I'll be scheduling it tomorrow, right? Yeah. Okay. Yes. So tomorrow the exam will be open tomorrow. It will be open from tomorrow morning. Please complete it by tomorrow. It will be available till 9 p.m. tomorrow. Please complete it. I hope you started working. So the seventh one, the question cannot be this simple, right? Find the area of the sector AOB. So to find the area of the sector, you need the sector angle and the radius. Theta by 360 into pi r square. Radius is known, but the sector angle is not known. So we need to first find the sector angle. So think, if you have to find something like this, think trigonometry. I've also given you the hint. Yes, you should have finished by now. What's the sector angle? No, we can't take this long. So looks like you have some problem in finishing. You see it here? Degree. Sector angle is 60, huh?
Yes,
Somewhat right, but incorrect. Here now, with respect to this figure, which is 60 degrees, AOB, is it?
yes, ma'am.
But do you think AOB can be, if AOB is 60, that means AOB will be an equilateral triangle, but the sides are 5, 5 and 5, root 3. They're not equal. No, all the sides are not equal. It cannot be 60.
Let me just second.
So you need to draw the altitude, connect this angle BOL with the opposite side and hypotenuse. Opposite side is 5 root 3 by 2. Hypotenuse is 5. So we get sine of angle BOL is equal to root 3 by 2. And when is sine root 3, sine of which angle is root 3 by 2, sine 60 is root 3 by 2. Sine of which angle is root 3 by 2, sine 60 degrees is root 3 by 2. So sine of angle BOL is equal to sine 60 degrees. So on comparing both the sides, angle BOL is equal to 60 degrees. So if angle BOL is 60, angle AOB will be twice 60 degrees, 120. And now the area of the sector, theta by 360 into pi r square. Yeah, please complete it.
Ma'am,
Yes,
once again, can you show the figure?
sure.
Thank you, ma'am.
Yeah. Show you the next question. So the next question, we are given the length. We are given that the length of the chord is 4 centimeters and the radius is also 4. The radius is 4 and the length of the chord AB is 4. In which case AOB is an equilateral triangle and hence the sector angle is 60 degrees. Length of the chord AB is 4 centimeters, radius 4 centimeters, which makes AOB an equilateral triangle, in which case angle AOB is 60 degrees. So to find the area of the sector, 60 by 360 into pi r square. Should finish the 7th one, take down the 8th question and complete it. I just told you about it. Nine and 10, both are simple. Yes, I'll wait for 10 minutes, finish all. 8, 9 and 10. Yes, are we ready with the answers for 8, 9, and 10?
No,
Okay, finish the 8th one.
yes,
Yes,
ma'am.
ma'am.
Okay, 9, doing the 9th one.
Yes, ma'am. Do
Yes,
it,
ma'am.
please.
Fine, yeah. Please complete 9 and 10. We shall discuss the answers. Yes, take down the 10th question. It's time to see the answers. Yes, what's the answer for the 8th one? What's the area of the sector?
8.380, ma'am.
8.380.
It's from 8.3.
All right, let's check. Okay. What about the 9th one? The perimeter is given. Find the area of the sector.
$45.30, ma'am.
45.30. Yeah, somebody said 8.3380, I think. This one was simple. Equilateral triangle, so the sector angle 60 degrees. All right. So here, the next one, the perimeter of a sector. So this is how a sector looks like. It's bounded by 2 radii and an arc. A sector is a piece of a circle bounded by 2 radii and an arc. And so we call the sector OAB. We've called this sector OAB. The radius is given. The radius is given to be 5.7 meters. And the perimeter of the sector is 27.2. So how do you express perimeter? It's 5.7 plus 5.7 plus L. Children, L represents the length of arc. L meaning the length of arc. L stands for length of arc. So here, L, length of arc in that particular sector. So in this sector, we have an arc here. This arc is called L, length. This is the length of this arc. Okay, so perimeter is radius plus length of arc, because R plus L is equal to 27.2. So working this, you get the value of L. And write down, children, there is another formula to find the area of a sector. It's given by LR by 2. You can do it now. Area of sector is equal to LR by 2. LR by 2. Please write down area of sector. You can find it in the, when you don't have the sector angle, you don't have to find it. Here we don't have the sector angle. You don't have to find it. You can use the formula. Area of sector is equal to LR by 2. L is the length of arc, R radius by 2. Area of sector is equal to LR by 2. Length of arc into radius by 2. So you can use this when you don't know the sector angle also. When you know the length of the corresponding arc and the radius, without the sector angle, you can find the area of the sector. Area of sector is equal to length of arc, L, R by 2.
45.0.
Yes. 45.03. Otherwise, if you want to find the sector angle, we know the length of arc. We know the length of arc is 15.8. So theta by 360 into 2 pi r is equal to 15.8. We need to work that. If at all you want to find theta, see, you don't have to do it. You can do this straight away, LR by 2. But if your question is how to find the sector angle, then since you know L is 15.8, how do you find the length of this arc? How do we find the length of this arc? Theta by 360 into 2 pi r. So theta we do not know, by 360 into 2 into 22 by 7 into r. That is so 5.7 is equal to 15.8. Children, we know that the length of this arc is 15.8. Equate this to theta by 360 into 2 pi r. So there theta is only unknown. You can work that and find the value of theta. And then find the area of the sector. So you can save your time. Remember this formula. Finding the length of arc, area of the sector. See, area of which sector? Area of that sector in which you have this arc, not some other sector. You have to find the area of the same sector in which we have this arc. So area of the sector is equal to the length of arc in that sector. Area of the sector, area of sector AOB is equal to length of arc in that sector AOB. Length of arc into radius by 2. So length of arc into radius by 2. These are objective questions, multiple choice questions. Now in the next one, ignore this number 17. I think it is question number 10. So for the 10th one, we are given the area of the sector 4.4. 4.4. We have to find the radius. We have to find the radius. We just have to use the formula, substitute the values in the appropriate places, and you see here the radius is 3. Please complete. All right. Yes, children, take down this question. A circle is inscribed. A circle is inscribed in an equilateral triangle ABC of side 12 centimeters, touching its sides. So the circle touches the sides of the triangle. The circle touches the sides of the triangle. It's an incircle. Find the radius of the inscribed circle. Find the radius of the inscribed circle and the area of the shaded part. And the area of the shaded part. The figure is given to us. Write the question, take the figure. Try it yourself first. So how do we, how do we initiate the thought process from where to think, what to think? So we have two figures here. We have one triangle and the other circle. Now for the triangle, it's enough if we have the side. It's enough if we have the side, and we know the side of the equilateral triangle is 12 centimeters. What else you need for the triangle? You can find area, altitude, whatever, perimeter, anything can be found using the side. So now then we have the circle. So for the triangle, meaning we have the side, so nothing much about the triangle. Now the circle, we need the radius of the circle. We don't have. So the first thing we have to, the question is also to find the radius of the circle. Even otherwise, we have these two plane figures, equilateral triangle, side known, circle, radius not known. So we have to first find the radius of the circle. So how to find the radius? You can recall this method we used yesterday. You can call this point. I'm just helping you get started. You can just call this point M or something. You can join OM. You can join OM, and then M is the point of contact of the tangent BC. M is the point of contact of the tangent BC. The sides of the triangle are tangential to the circle. The sides of the triangle. Am I audible, children?
Yes, ma'am.
Yes.
Yeah. The sides of the triangle, the three sides of the triangle are tangential.
Ma'am.
They act as tangents to the circle. All right. So let's just take up this tangent BC. The side BC which acts as a tangent. Let's mark this point M. Let's mark this point M. Let's join OM. And we know that OM will be perpendicular to BC because radius tangent at the point of contact perpendicular to each other. So OM will be perpendicular to BC. Then join OB. So that way we have an equilateral triangle. That way we have an equilateral triangle. And then since this angle is 60 degrees, this angle OBM will be 30 degrees. So now we have a right triangle. Now we have a right triangle in which one angle, this angle is 30 degrees. And then, sorry, in which one angle is 30 degrees, one acute angle is 30 degrees. And you know that BC is 12 centimeters. So BM will be half of BC. BM will be half of BC, 6 centimeters. So in the right triangle, you have angle 30 degrees, you have BM 6 centimeters. Yeah, now you need to understand what to find. You need to find the radius, which is OM. You need to find the radius, which is OM. So use trigonometry and connect the known things with the unknown. Connect 30 degrees, which you know, 6 centimeters, which you know, with the unknown. You need to find the radius OM. Connect it with OM. Use a suitable trigonometric ratio and connect the known with the unknown. Yeah, and that way you'll find the radius and then find the area of the shaded region. Yes, try. Work and share your answer on WhatsApp, children. I want you all to get this right. We have seen how trigonometry is applied to find angles or sides earlier. You can use a different method also. This is just one of the ways of getting it. You can use a different method in case you want to. Like you can use, I can just suggest, if you want to know what is that other method, you can even consider the median. You can consider the median, and O is the centroid. It divides it in the ratio 2:1. So you can use that idea also and proceed. You can use the idea of the centroid dividing the median, the ratio 2:1. You can just try that, because you know the side of the equilateral triangle. Using the side, you can find the altitude. You can find the altitude, and altitude is the median. So you can use that idea also.
Ma'am, can you check my answer?
Yeah, I'm just having a look, Srinivasan. Tan 30 is opposite. Perfect. Perfect, Srinivasan. So you found the radius. Now go on to find the area of the circle. We have to take pi as 3.14. Proceed to find the area of the circle. And then you know how to find the area of the shaded region. Area of the circle minus the area of the triangle.
Root 3 is 1.73 or 732.
If nothing is mentioned, 1.732. Okay, pi
Okay.
3.14 was for a different one. I'm sorry, I had a different slide. I think we're doing this one, yes. So here pi is not 20, nothing is mentioned, so 22/7. Yes, only Srinivasan has got the radius. What about the others? Nafi has shared.
Got the radius.
Please share the picture, child. Please share the picture. Very good, Nafi. Your procedure is right. That's what I said. There is more than one way of doing this. You're right, Nafi. Good. Okay. So this is that other method, which you see here. We're using the property of the centroid and the median. Using the property of the centroid. What I had asked you to do is join OB. I told you this one. I also mentioned about the second method, that the second method is what you see here. We know that AO is to OM is equal to 2:1. AO is to OM is 2:1, which means OM is OM is 1/3 of AM. OM is 1/3 of AM. AO is 2/3 of AM. AO is 2 parts, so 2/3 of AM. OM is 1 part, 1/3 of AM. So OM is 1/3 of AM. So OM is a radius. Why are we interested in OM? OM is a radius. OM is the radius of the in circle. So OM is equal to 1/3 of, how much is the AM? AM is √3/2A. AM is √3/2A. Because AM is the altitude of the equilateral triangle. AM is the altitude of the equilateral triangle. So AM is √3/2 into A. A is 12. So like this, you can find the radius, 2 √3.
I have sent my answer now.
Yeah, let me check. So the first method I told you, you can just get a right triangle here, connect 30 degrees with OM, the radius, and BM, which is 6. So that way also you can get this answer, OM 2 √3. This is the other way. This is the other way. Any doubt with this one, children? The radius is 2 √3, and once you find the radius, once we find the radius, find the area of the triangle, find the area of the circle, difference will give you the area of the shaded region. Difference will give you the area of the shaded region. Area of the triangle, you can see it here. Area of the circle. The difference is the area of the, the difference is the area of the shaded region. Yes, Shakti, you're right, but I'm not able to see some portion of the answer I think is missing, but I'm sure you've understood it correctly.
Okay, ma'am.
Shani. Yes. Yes, your radius is right. Good, Priyadarshini. So I have it from Srinivasan, Nafi, Shakti, and Priyadarshini. Good children. The others are also good, but I don't know if you're finished. All of us are good. Please
Ma'am,
work
for
on.
me, I got the correct answer at first, then I was cross-checking and then I got confused, ma'am. That's why I didn't share the picture.
Okay, okay. Any clarification? Should I help you in some way?
No, ma'am, the first one which I did was right only, ma'am.
Okay, nice. Okay. So what you can also do is, let me use the question and tell you. Listen to the A third method, children. Listen to me carefully. Now, can we call the points of contact? Let's look at AB, BC, and AC as tangents. All right. Let's look at AB, BC, and AC as tangents. All right. Now let's call this point P. Let P be the point of contact of the tangent AB. Let the tangent AB meet the circle at P. Let the tangent BC meet the circle at Q. And let the tangent AC meet the circle at R. So we are marking off these points P, Q, and R. Now what happens when you join OP? When you join OP, since your OP is a radius, through the point of contact. From the point of contact, it's a radius. So the radius and the tangent at the point of contact are perpendicular to each other. So OP will be perpendicular to AB. Similarly, OQ will be perpendicular to BC, and OR will be perpendicular to AC. OP, OQ, OR will be perpendicular to AB, BC, AC respectively. Next, join OA. That is, we are going to divide the triangle into three smaller triangles. We are going to divide the triangle into three smaller triangles. So let's join OA. Let's join OB and OC. Is that fine, children? Join OA, join OB, join OC. Do all this in your book. Do this. Make a rough figure fast. Draw the encircle. Take OP, OQ, OR, and then join OA, join OB, join OC. Keep it ready. Harshita, very good. Yes, Parkavi, we are discussing that method now. You can just check if you worked it correctly. Parkavi has also shared her answer. Okay, I think it should be ready now. Now, write down, children. Area of triangle ABC is equal to area of triangle ABC is equal to area of triangle ABC is equal to what? Area of triangle AOB plus area of triangle BOC plus area of triangle AOC. The area of the whole triangle ABC is equal to, this is the equation we are writing in words. Area of, see, you need to have some equation to substitute and find the value. So the equation is area of the whole triangle ABC is equal to area of the triangle AOB plus the area of the triangle BOC plus the area of the triangle AOC. Now area of triangle ABC we know is √3/4 into side square, √3/4 into 12 square. Okay, then what about the areas of the smaller triangles AOB, BOC, and AOC? Okay, so they'll be half base into height. Half base AB into height, this one OP, which is the radius, which is R. See here, OP is R, OQ is R, R is also R. We have called them P, Q, and R, right? We have called them P, Q, and R. OP is R, OQ is R, and OR is R. That is the altitude of the three triangles, the three smaller triangles. The altitude of the three smaller triangles are equal to the radius of the encircle. Okay, so area of triangle AOB is equal to half base into height, half into base AB, which is 12, into height, which is the radius, into R, half into 12 into R. Similarly here, half into 12 into R, same thing. Here, half into 12 into that is half base into height everywhere, children. Half into base, which is 12 into height r. So that means you will get root 3 by 4 into 12 square is equal to half into 12 into r plus half into 12 into r plus half into 12 into r. So half into 12 meaning 6r. So you will get 6r plus 6r plus 6r. So 18r. So root 3 by 4 into 144, that is. Please work that, okay? So root 3 by 4 into 144 is equal to 18r. 18r, 6r plus 6r plus 6r, 18r. All of you please work this and get the value of r. You should get 2 root 3. This is another method. So you can use trigonometry. You can use the property of the centroid. You can use this method. This method is dividing the whole triangle ABC into 3 smaller triangles. And the equation is area of the whole triangle is equal to the sum of the areas of the 3 smaller triangles. Yes, children, work out. See, don't think, okay, you know one method, why waste time in other two? You're getting different ideas. Ideas
Yes, ma'am,
important.
it's 2 root 3.
Yeah, very good. Okay. These are the different ways, so different ideas. So when you revise this tomorrow, you must tell yourself, you must revise like this. What are the different ways of finding the radius? So one is by making a right triangle here and using trigonometry. Other is using the property of the centroid, 2:1 ratio. Now this method, dividing the whole triangle into 3 smaller triangles. All right. Please complete that. You must get, it's enough if you find the radius. Radius is equal to 2 root 3. You must get the same thing there. Yes, children, try this now. An equilateral triangle ABC of side 6 centimeters. So here again, the side is given to you. The side of the triangle has been inscribed in a circle. Find the area of the shaded region. So again, we know the side of the triangle. We do not know the radius. We do not know the radius of the circle. So we just have to find the radius of the circle. Right? Parkavi, the earlier one you have asked me if it is right. Yes, so you're right. But one thing is, radius is 2 root 3. There you should not use the value of root 3 1.732. You should not use it there. That's the correction. You found R is 2 root 3, Parkavi, and then 2 root 3, 2 into 1.732. That you should not do. Okay, even if you did that, you should not use that value for further calculation. Okay. You should not use, you must use R as 2 root 3 because R square will be 3 4s are 12. If you use the decimal value, you lose the perfection.
Okay.
Yeah. Good, Arna.
Ma'am.
Yeah.
Can you show the second method of the answer, ma'am? 11th one, the previous
11th.
question.
Okay, what is on the what I showed you earlier? Is it?
Yes, ma'am. The second method.
I think this one. Yeah.
Yes, ma'am. Got it, ma'am. Thank you. I took the screenshot.
Okay, this one is it? This 9th one, right? Okay.
Ma'am, I took the screenshot.
Right on it. Good, Manasa. Very good. Yes, what's the radius of the circle?
Ma'am, 2√3.
Same thing, 2√3. Which method have you used? Which method, meaning how have you got this value 2√3?
Ma'am, using the altitude.
Using the altitude, meaning using the ratio 2:1, is it? You can see it here. So you can use this property. Again, you can use trigonometry also, children. You experiment all that. You can also use trigonometry. So here you see we've used the ratio 2:1. But here we should not find OM. OM is not the radius. OA is the radius. That's the difference. The difference between the earlier one and this one is, in the earlier one, we had to find, that's the difference. Note that difference. In this one, where the circle, please listen. In this one, where the circle is an in circle, OM represents the radius. OM represents the radius, not OA, not OA. So we have to work 1/3 of AM. We'll have to find OM, which is 1/3 of AM. While in this one, AM is the median, equilateral triangle, AM median, O is a centroid. So the centroid divides the median and the ratio 2:1. So here we have to find AO, not OM. OM is not the radius of the circle. AO is the radius because O is a circumcenter and A is the point on the circumference of the circle. So OA is the radius. So we need to find OA. OA is 2/3 of AM. OA is 2/3 of AM. So OA is equal to 2/3 of AM is the altitude, which is √3/2A. AM is the altitude, which is given by the formula √3/2A into 6. So OA is 2√3. So like this, we find the radius like this. So important, don't find OM. It's not relevant. We need to find OA, which is the radius of the circumcircle. And then, you have to find the area of the circle, find the area of the triangle. You know the radius, so you can find the area of the circle, area of the triangle. The difference will give you the area of the shaded region. The rest of it in this we have already discussed, this and this. Okay, so this is similar. This is a regular hexagon, and you can see a circle inscribed. Circle is inscribed in the regular hexagon, and here a circle circumscribes in this figure below here. Here a circle circumscribes a regular hexagon. A regular hexagon is circumscribed by a circle. You know that a regular hexagon is made up of 6 equilateral triangles. A regular hexagon is made up of 6 equilateral triangles. Now, this being the circumcenter, that is the center of the circumcircle. This being the center of the circle, when you join O to A, O to B, O to say C here, O to D, O to E, and O to F, you will get 6 triangles. The 6 triangles are equilateral triangles. So, to find the formula to find the area of a regular hexagon. See here, a regular hexagon is made up of 6 equilateral triangles. Area of regular hexagon is equal to 6 into √3/4 into side square. That is the side of the hexagon. √3/4 into side square. A regular hexagon is made up of 6 equilateral triangles. Area of a regular hexagon, not every other hexagon. Area of a regular hexagon, because a regular hexagon is made up of 6 equilateral triangles. Area of one triangle is √3/4 into side square. So into 6 will give us the area of the regular hexagon. So this is the form. This is how we find the area of the regular hexagon, and area of the circle, then you have to just subtract to find the area of the design. I'll share these two answers, children, the question and answers. And here you're given, I'm just reading out from here, and in this figure you're given, this is the next one. Actually, it's not another question. I've just given, see here, you can see it, note, in case the circle is inscribed in the regular hexagon, then how do we handle it? I just mentioned that here. So supposing you're given the radius, OM will be the radius, OM is the radius, and you know that AB is the tangent, and OM radius, AM tangent, so 90 degrees. Radius perpendicular to tangent, radius perpendicular to the tangent at the point of contact. So 28, the radius OM is given to be 28. The radius OM is 28. So when you know the radius of the circle, we have to find the side of the hexagon. We know the radius of the circle. See, there are only 2 figures here, hexagon and circle. We know the radius of the circle. Then we have to find the side of the hexagon. So again, trigonometry. You can use trigonometry. You can see it here. because this is made up of 6 equilateral triangles. You can see one triangle here. You can see one equilateral triangle here. A regular hexagon is made up of 6 equilateral triangles. You can see one of it here. And since it's equilateral, this angle is 60 degrees, so half of it 30 here. Congruent. These two are congruent triangles. This is the equilateral triangle AOB. This is one of the 6 triangles that are formed in a regular hexagon. See, our intention is to find the side of the hexagon, and we're using trigonometry. So you have a right triangle here. You know this angle is 30 degrees. And you know the radius. So you'll have to find AM. Use trigonometry and find AM. And if you find AM, or you can find AM and double it, or you can find OA straight away. That's what I've worked here. You can connect 30 degrees with OM, which you know, and OA, which you need to find. You can connect 30 degrees, the acute angle 30 degrees in the right triangle with OM, which you know, 28 centimeters, with OA, what you have to find, the side of the equilateral triangle or the side of the hexagon also. Because all the sides are equal. There's an equilateral triangle. OA is also AB. Whatever is OA is also, see it, OA is not the radius. OA is not the radius of the circle. You can see it. It's not the radius. OA, AB, and OB all are same because it's an equilateral triangle. So you can also find OA, which will be AB. So right triangle, 30 degrees. Because the whole angle is 60, equilateral triangle, 30 degrees. And then you know OM is 28 centimeters. Find OA, cos 30, because adjacent by hypotenuse. For 30 degrees, AM is the opposite side. For 30 degrees, AM is the opposite side. So OM is the adjacent side and OA is the hypotenuse. OA is the hypotenuse, that we know because it's opposite in the right angle. OM is the adjacent side. So this I'll share the pictures. So we have seen a square. A square is a regular polygon. We have seen a circle inscribed in a square and a square inscribed in a circle. And then equilateral triangle, a regular polygon. Equilateral triangle is, see, we have seen regular polygons, equilateral triangle, square, and regular hexagon. These 3 figures. Are we listening, children?
Yes,
Are we
ma'am.
there? Yeah, so we
Yes,
have,
ma'am.
all right, children, thank you. So these 3 regular polygons, equilateral triangle, square, regular hexagon. We have seen a circle inside and outside these. I'm just telling you in simple words. So when you take the triangle, equilateral triangle, we have seen a circle inside the triangle and outside the triangle. That is incircle and circumcircle to the equilateral triangle. Then for a square, we have seen both the situations. A square and a circle inside it, and a circle with a square inside it. All right. Okay. Now this one, a regular polygon, regular hexagon. You can see the circle outside the hexagon, and in the next one you can see this hexagon outside and the circle inside. Here the circle is inside. Here the circle is outside. So here the hexagon is circumscribed by the circle. Here the hexagon circumscribes the circle. The hexagon circumscribes the circle. This also is, we've discussed similar situations. So I'll share this answer. This exactly the same thing I think we have worked in the class. Exactly this we have worked in the class.
Yes, ma'am.
Yes,
On
ma'am, on
18th.
18th.
Oh, thank you so much. Yeah, yeah, okay. So let's take up something new from this. Yeah, let's try this one because these situations we have seen already, children. Not all in this we have to work. I'll just tell you. I'll just select the ones which we need to work. We've finished this one. This I think we discussed in the class the other day. I don't know if we worked the answer. Let's see. Okay, we'll start with the 12th one, children. Let's start with the 12th one. Let's start with the 12th one. So what you see, you can see this one. No.
13th one. 13th one.
13th. Okay, 13th. We worked the answer also, or we only discussed the procedure. We worked it.
Ma'am, worked the answer also.
All right. Thank you. Thank you. All right. So the 12th one, children, you see a semicircle. This one is a semicircle with BC as diameter. This is a semicircle. This arc is a semicircle with BC as diameter. This arc is a semicircle with AB as diameter. And this arc is a semicircle with AC as diameter. So in other words, ABC is given to be ABC is a triangle. Even if it is not given, it's a right triangle. I'll tell you, it will be a right triangle. Okay. So here, since I've marked, ABC is a right triangle with each side of the triangle as diameter. Semicircles are described. That's what it is. That's what is this situation. Triangle ABC, right triangle ABC, right triangle ABC, right angle at A, with BC, AB, and AC, with the three sides of the triangle as diameters, semicircles are described. Or semicircles are described with the three sides as diameters. So with BC as the diameter, this is the semicircle described, this semicircle. Now this semicircle stands on the diameter AB, and this semicircle stands on the diameter AC. So given this, we need to find the area of the shaded region. Area of the shaded region. And this one will be a right angle because angle in a semicircle is a right angle. Because if BC is the diameter, if BC is the diameter and this is a semicircle, this has to be 90 because angle in a semicircle is a right angle. So even if angle A is not marked 90 degrees, you know it is 90. Because it's given, this one is a semicircle. If it's a semicircle, there's the diameter. If there's the diameter, then this is 90 degrees. Because the angle in a semicircle is a right angle. Yes, work this, children. Yes, I want you to work 4, 5, 6, 7, and 12. Children, you must work 4, 5, 6, 7, and 12. Start with the 12th one. Start with the 12th one. Complete 12th one, then try 4, 5, 6, and 7. Can anyone tell me the idea? Meaning that way which we can arrive at the area of the shaded region. Now, let's try to answer this question, children. Supposing the entire thing is shaded. Supposing I share whatever figure you see that the entire thing is shaded. How will you find the area of the entire shaded region? Suppose I shade all this, and whatever you see here, this entire thing is shaded. Okay, the entire thing is shaded. How will you find the area of the complete shaded region?
Area of triangle plus area of two
Area of
semicircles.
triangle plus area of two semicircles, ma'am.
Semicircles, very good. So area of the triangle, so area of this triangle, plus the area of this semicircle, plus the area of this semicircle. See here, it's like first you just imagine three pieces, you place this triangle first, that is the first piece. Then you place a second piece, which is this semicircle, and the third piece, which is this semicircle. When you put these three pieces together, you get the entire figure. Imagine that this entire thing is made up of three pieces, triangle, and then triangle, the first piece triangle, second piece the semicircle with AB as diameter, then the other piece, the third piece is this other semicircle with AC as diameter. If you bring these three pieces together, you get the entire figure which you see here. Now from this, so when you find the area of the triangle plus the area of this semicircle plus the area of this semicircle, you get the area of the entire thing. From that, what should you remove? What should you subtract to get the area of the shaded region? What should you subtract to get the area of the shaded region? From that,
Area of the semicircle.
yeah,
The big
from that,
semicircle. ABC.
yeah, you should take away the area of the semicircle with what as diameter? With
BC.
with BC as
BC,
diameter.
ma'am.
That's all it is. So find this is again one way of doing it. You can find the area of the whole thing. The area of the whole thing is area of the triangle plus the area of the two semicircles with AB and AC as diameters. So from that, step one, find the area of the triangle. Step two, find the area of this semicircle, half pi r square. Then step three, find the area of this semicircle. Again, half pi r square, radius is different. Add these three, you will get the area of the total figure. Then find the area of this semicircle with BC as diameter and subtract area of the entire figure minus the area of the semicircle. See, when you remove the semicircle, you're removing the unshaded region. From the whole thing, if you remove the unshaded region, you're removing the unshaded region. From the whole thing, see, the whole figure is made up of two things, shaded and unshaded region. From the whole thing, if you remove unshaded, you'll get area of shaded region. From the whole area, from the complete area, if you take away the area of the unshaded region, you will get the area of the shaded region. So if you take away this unshaded area, semicircle, you will get the area of the shaded region. Do it. Find BC. How do we find BC? How do we find BC?
Using the Pythagoras theorem.
Yeah, using Pythagoras theorem. And for the sixth one, what is 1 hectare? What is 1 hectare? An area of 1 hectare is equal to
10,000 meter, ma'am.
10,000 meter? 10,000
Meter square.
meter square. Okay, I think that is a guess. Meter square. 1 hectare. Hectare is a unit for area, not for length. Hectare is a unit of area. 1 hectare is equal to 10,000 meters square. An area of 10,000 meters square is called 1 hectare. Yes. Now you shouldn't have any more doubts. I'll just get back in some time. So 12 we've discussed, children. Work the 12th one, 4, 5, 6 and 7. We'll see the answer at the end of some 10 to 15 minutes. Please write the question and then work the answer.
Ma'am, I've shared the answer.
Yeah. No, I haven't got it, ma'am. Yeah, I just got it. I just got 2. Yeah. Let's just discuss the answers first. Yeah, Arnav and Shakti's shown. Have you sent all the answers? No, only one I can see some calculation. Okay, Arnav has shared his answers. Fine. What's the answer for the 12th one, children? What's the area of the shaded region?
442.85.
Please come again. 4?
290.
Okay.
294, ma'am.
Okay, let's just see. Yeah, so here we have. Is BC 35? Did we all get BC 35?
Yes,
Yes,
ma'am.
ma'am.
Area of the triangle, half base into height, 294 centimeters square. Area of the triangle is 294. Area of the semicircle with diameter AB is 173.25. And the area of the semicircle with diameter AC is 308. Have we got these values?
Yes, ma'am.
So first we have to find the area of the length of the hypotenuse, and then area of the triangle and the area of the 2 semicircles. And here I've also found the area of the semicircle with BC is diameter. Diameter, see again, if you've taken the diameter as a radius by mistake, I think that's why most of the students are quite. I assume that you've taken the diameter as a radius and so you have not got the correct answer. Srinivasan was the only one who said yes. Okay, so find the area of the semicircle, and then as we discussed, the area of the triangle plus the area of the 2 semicircles minus the area of the semicircle will give us the area of the shaded region, which is 294. Did we get this, children? 294 exactly.
Yes, ma'am.
Yes,
Okay.
ma'am.
Okay, children. Nice. All right. See, nothing difficult. First, it's a semicircle. So half pi r square. Semicircles, 3 semicircles. So everywhere half pi r square. And radius, what you see in the figure are diameters. So radius, everywhere half of the diameter you see. That's all. You just have to be careful in writing the formula half pi r square and in using the value of the radius, half of the diameter. That's all. Yeah, how many revolutions, children? Let me see how many correct answers I'm going to get. What's the answer for the 4th one? The final answer?
Ma'am, 7 revolutions.
2375.
This is similar to a question in NCRT. Similar question.
438.
Ma'am, 4375.
4375, ma'am.
4375. I heard another answer. What was that?
438.
438. This is similar to the to a question in NCRT. I think the first exercise, the 4th one, if I'm not wrong, the 4th or the 5th one. Similar one we have there. I think there also the speed was 66 kilometers per hour. Only the diameter is different here, I think. Okay, 4375. Let's see if let's get all the answers, because when I show the 4th answer, I think the 5th and 6th also will be visible. Okay, let me note down. So I got it from Priyadarshini, I think Arnav, 4375 for the 4th one. What about the 5th one? What about the 5th one?
260.
264.
ma'am.
Okay, what is the sector angle, children? What is the sector angle?
210.
200
200 and
210 degrees.
210.
210 degrees. Okay.
Ma'am?
Okay, and the area of the sector?
264 centimeters
264.
square.
Okay, fine. And what about the sixth one?
100 meters.
100 meters.
100 meters. The length of the diagonal. Okay, so the area is 0.5 hectares, which means 5,000 meters square, because 0.5 is half a hectare. 1 hectare is 10,000 meters square. Half a hectare will be 5,000 meters square. 5,000 meters square. The area is given. 5,000 meters square is the area. So we need to find the length of the diagonal. Okay, what's the answer you got for the sixth one? What's the length of the diagonal?
100.
100, you said. Okay. And I think you were asked to work the seventh also. Yeah. What's the answer for the seventh one? Perimeter of the sector? No, area of the sector.
280.
280 centimeters square.
280 centimeters square. Did we use LR by 2?
Yes,
Yes,
ma'am.
ma'am.
Yeah, LR by 2. LR by 2. Length of arc. You have to find the area of the sector. So the length of the arc in that sector. Length of arc into radius divided by 2. LR by 2. Length of arc into radius by 2 will help you find the area of the sector. And that's 280. So now let's see if these answers are correct. The fourth one. Yeah, 4375 is right. So this is this is for, a situation like in the fourth one. If you write this equation in words, you can answer any question. If you can write this one, the circumference of the wheel into the number of revolutions will be the total distance covered. This is the equation. The circumference of the wheel, that is a distance covered in one revolution, into number of revolutions, the total distance covered. Now to find this total distance covered, it's speed into time, because distance is speed into time. See, we are finding every part of this formula. This acts as a formula. This one will enable us to get the answer. Distance covered in one revolution into number of revolutions is the total distance covered. Now, how do you find the total distance covered? Speed into time. So it's so many centimeters. And how do we find it? Why do we convert this to centimeter? Because the radius is in centimeter. Radius is in centimeter. Circumference 2 pi r. So here, like this. Now substitute in this formula. Circumference is 1760 by 7 into the number of revolutions n is equal to 11 followed by 5 zeros. Since the circumference is in centimeter, meaning the radius is in centimeter, you have to convert this total distance also to centimeter. The unit should be the same in one equation. You cannot have meter and centimeter in the same equation. So this is the rule, children. This is the formula. Now find the circumference of the wheel, have it as a fraction, then find the total distance covered in centimeters, substitute in this formula and get the number of revolutions. 4375. Yeah, so you can also, okay, that's about the fourth one. And this one, children, you can also use a proportion. I don't think I've mentioned this in the class. You can also use this proportion. See how do you understand? Read this proportion. The minute hand goes 60 minutes. In 60 minutes, when this minute hand goes 60 minutes, it covers 360 degrees. In 35 minutes, how many degrees? Proportion. You can also do it like this. The minute hand, this is about the minute hand. This is about the minute hand. 60 minutes, 360 degrees. 35 minutes, how many degrees? 60 minutes is to 360 degrees. is as to 35 minutes is to how many degrees? 60 minutes, 360 degrees. 35 minutes, how many degrees? Okay, so then you know product of extremes is equal to product of means. Product of extremes is equal to product of means, and yeah, x is 210. Yes, I got this answer from you. X 210 and the area is 264. Yeah, I heard this also from you. Very good. 210 is correct. 264 is also right. Very good. So here, yeah, 100 meters. Somebody said 100 meters. I think Arna, correct?
Yes, ma'am.
Yeah. You can also use a formula if you want to use this formula. Area, that is, we need to find the diagonal, right? Okay. So you have this formula, no? Area is equal to half d square. You have the area here. You have the area here, area of the square. Area of the square is equal to half diagonal square. Formula. Area of square is equal to half d square. Half diagonal square. Area of square is equal to half d square. Diagonal square. Half d square. So 5,000 is equal to half d square. 5,000 is equal to half d square. So what will you get? 10,000 is equal to d square. D is equal to square root of 10,000, which is 100. You can also do it like that. You can use the formula. Area of square is equal to half diagonal square. Half diagonal square. Area of square is equal to, see, area of square is 5,000. Now this 5,000 area is equal to half d square. You can also do that.
Ma'am.
Yeah.
As a square is divided into two square, we can take as 2,500 as a area of one square, and by Pythagoras theorem, can we find the
Yeah. You have same two triangles you need. Two triangles you need. Square you can divide. The diagonal divides it into two triangles. Yeah, you're right.
Yes.
Two congruent triangles. Yes, you're right. You can do that. Pythagoras theorem. Yes. All right, children. So this is what it is. So area of square is 5,000, and then I have here found the side and then the diagonal. Diagonal is root 2a. Seventh one, very important. Seventh one, because sometimes we misinterpret this. Perimeter of the sector is 68. Perimeter is 68. Perimeter. That means R plus L is equal to 68. So from that we get L. And once you find L, area of sector is equal to LR by 2. LR by 2, 14 to 14. Radius 14 by 2. 280 centimeters square. This answer also I got from you. Very good. Very nice, children. All right, children. So that's it for today's session. Thank you so much. 1 minute class. Use the emoji. Raise your hands. Use the emoji. Raise your hands, class. See, only 19 of us at 9:10. See? Okay, I appreciate these 19 students. Very good. All right, children. Thank you so much, children. So that's it for today's session. If you have any questions, stay back, else you may leave the meeting. Thank you. Good night.
Thank you, ma'am.
Thank you.
Thank you, ma'am.
Thank you.
Thank you.
Thank you, ma'am.
Thank you, children.
Thank you, ma'am.
Good night.
Thank you, ma'am.